Hello everyone, welcome to our today's presentation. The title of the presentation is Backtracking Search Algorithm for PV Module Electrical Parameter Estimation. Most of the contributing authors of this article are from King Fahd University of Petroleum and Minerals at Dhahran, Saudi Arabia. Only Dr. Asif Islam, who is currently working as a test engineer at Noosa Power Switchgear Limited in Brisbane, Australia. Myself, Dr. Mohammad Shafiullah, who is currently working as a researcher in the Center of Research Excellence in Renewable Energy at King Fahd University of Petroleum and Minerals. Since the inception of Kyoto Protocol, the research and investment in renewable energy technologies have been increased manifold. The decision makers from all over the world are trying to meet the energy demand from safe, secure, and environment-friendly resources. In response, the world is observing a surging growth of renewable energy technologies, especially the PV technologies and their grid integration. According to REN21 reports, the world capacity for PV system has been raised to 627 gigawatts as of 2019. Anyway, the PV modules are represented by equivalent electrical models. Precise information of the model parameters play a critical role in estimating the power yield from the PV system at different ambient conditions. In general, the PV modules are modeled using 3-parameter, 4-parameter, or 5-parameter models. The 5-parameter models showed better accuracy in terms of predicting output power at different ambient conditions. The PV modules are also represented by 7-parameter models, which is a bit computationally expensive. Therefore, the 5-parameter model gained huge popularity due to its simplicity and accuracy. Irrespective of the electrical models of the PV system, it gives us a current and a voltage. However, the 5-parameter models of the PV system can be represented by these equations, where IPV stands for the terminal current and VPV stands for the terminal voltage of the PV module. IL is the photo-generated current, ISAT is the dark saturation current, RS is the PV module series resistance, RSH is the PV module shunt resistance, and A is the modified ideality factor. ISH is the shunt branch current, ID is the diode current, K stands for Boltzmann constant, and N stands for diode ideality factor. Q is the electronic charge, NS stands for number of series connected cells, T represents PV module temperature, and VTH stands for thermal equivalent voltage. Amongst the mentioned parameters, the VPB and IPB are the output of the PV panels, and the parameters of this box are either constant or can be calculated using formula. However, the parameters of this red box are the 5 parameters that needs to be estimated to calculate efficiently the output power of a PV systems at different ambient conditions. Now the question is, why do we need to estimate those 5 parameters? If we are going to estimate these 5 parameters, what are the informations provided by the PV manufacturers? These are the nameplate informations provided by the PV manufacturers. For example, Docu Solar, BP Solar, Canadian Solar, Zinco Solar, Blue Sun Solar, Solar World, and so on. As you can see from the nameplate information of the Docu Solar, they are providing the model number, maximum power voltage, maximum power current, open circuit voltage, short circuit current, and so on. However, they are not providing the 5 parameters of the PV electrical equivalent model, as PV models can be represented by 3-parameter, 4-parameter, 5-parameter, or 7-parameter models. The PV module current is represented by this equation. This equation is a nonlinear equation that cannot be solved using linear equation solving techniques. Such nonlinear equations are solved using either analytical or numerical approaches throughout the years. However, the analytical approaches are based on assumptions, and those assumptions can lead towards wrong estimation of the parameters. Therefore, different numerical approaches like the genetic algorithm, particle swarm optimization, differential evaluation have been employed in the literature to estimate the PV module parameters. In this research, we have employed a numeric technique called backtracking search algorithm to estimate PV module parameters. Now let us go to the problem formulation sections. As you can see, these are the IV characteristics and PV characteristics of the PV module. Using manufacturer data at 3 different points, we can have 3 equations. For example, the open circuit data, short circuit data, and maximum power point data. Still, we need two more equations to solve the 5-parameter model of the PV module. The fourth equation can be derived from the maximum power point, as dP over dV equal to 0 at that point. Similarly, the fifth equation can be derived from the reciprocal of the slope of the IV curve. The nonlinear equation at short circuit point can be written using these equations, where the value of F1 should be close to 0 or equal to 0 for a perfect model. Similarly, the equation for F2, F3, F4 and F5 can be derived from other four equations. Now, for a perfect model, the summation of F1, F2, F3, F4 and F5 should be equal to 0 or close to 0. Therefore, the objective of this parameter optimization problem is to minimize the summation of F1, F2, F3, F4 and F5. And the values of the parameters should be selected from their minimum and maximum ranges. It was stated earlier that this research employed the backtracking search algorithm to estimate the PV module parameters. The algorithm consists of several steps. In the first step, it initializes the initial population and historical population using the given equations. After generation of the initial population, the BSA evaluates the fitness of all individuals of the initial population. Based on the evaluated fitness, it stores the best individual as the global best solution. The second step of the backtracking search algorithm is known as selection 1. In selection 1, it updates the historical population using the given equation from the historical population as well as from the initial population. Mutation is the third step of the backtracking search algorithm. During the mutation, it generates a mutant vector from the initial and the historical populations using the given equation. After the mutation operation, some of the control parameters may go beyond their pre-specified ranges. The BSA uses this equation to bring them back into the search space. The fourth step of the backtracking search algorithm is known as crossover, where it updates the mutant vector from the primary mutant vector and the initial population using this equation. In the fifth step, it evaluates the fitness of the individuals of the final trial population. Then it updates the individuals of the initial population from the final trial population and the initial population based on their relative fitness. Then the BSA updates the global best solution if requires. Finally, the BSA checks the termination criterion. If such criterion are fulfilled, then it stops the algorithm. Otherwise, it goes back to step number 2. It is important to mention here that the mutation, crossover and boundary control mechanism of the backtracking search algorithm are different from other evolutionary algorithms, including the genetic algorithm and differential evolution. This is the flowchart of backtracking search algorithm, which starts with the generation of initial and historical population and ends with providing the best solution for the optimization problem under investigation. In this research, we have employed the backtracking search algorithm to estimate the parameters of three different PV module technologies, such as monocrystalline, poly-crystalline, and thin film. This table summarizes the datasheet values of three different PV module technologies. Here we have the values of short circuit current, open circuit voltage, maximum power voltage, maximum power current, maximum power, and number of cells in series. This is the objective function convergence curve for the polycrystalline technology obtained using the backtracking search algorithm. As can be seen, the objective functions have been converged to certain numbers which are close to 0 in different runs. We have also observed similar objective function convergence curves for other PV module technologies. It was stated that we have estimated 5 parameters of 3 different PV module technologies using the backtracking search algorithm. Estimated 5 parameters are photo-generated current, dark saturation current, modified ideality factor, PV module series resistance, and PV module shunt resistance. Based on the BSA estimated parameters, we have calculated the maximum power of 3 different PV module technologies. Then we have compared them with their datasheet values. As can be seen, the calculated and the datasheet provided maximum power values for 3 different PV module technologies are very close to each other. Also, the evaluated error percentages are very minimal, which demonstrated the efficacy of the backtracking search algorithm in estimating PV module parameters. We are now at the final part of this presentation. In this research, we have employed the backtracking search algorithm to estimate the 5 parameters of 3 different PV module technologies. Objective function convergence curves for different runs confirmed the robustness of the proposed approach. Datasheet provided and calculated maximum power comparisons for 3 different PV module technologies validated the efficacy of the proposed approach. That's all from our side. Thank you for listening.